So today we're going to look at the continuous uniform distribution. Now, if you just think what it means to be uniform in terms of a distribution, it means each outcome has the same probability of occurring. So the first uniform distribution you came across was a discrete uniform distribution, and it would likely be rolling a dice, where each outcome had the same probability of happening. Each outcome was 1/6. And if we were to draw that, that would be 4 vertical lines, all of the same height, all representing the same probability. For the continuous uniform distribution, it's the same situation, except we have a continuous range of potential outcomes. This means that our diagram is this horizontal line. The horizontal line being the same value for all of the outcomes in between A, which would be the lowest possible outcome, and B, the highest possible outcome. Okay, there's some things we can deduce from this diagram. Firstly, we know for this to be a valid PDF, the area represented underneath this function should equal 1. If we know the area equals 1, we can find out what the fx value is going to be. We can find out what the height is going to be. This is a rectangle, so one of the simplest area formulae you know. The width times the height should equal 1. The width is the difference between B and A, so that's B minus A. I'll multiply that by our function, and that should equal 1. Rearranging, we get that the function equals 1 over B minus A. For a continuous uniform distribution, the value of the function is 1 over B minus A. In general, we can describe this continuous uniform distributions PDF just like this. As soon as I tell you the values of A and B, you should be able to put together the PDF function. There are some features of the continuous uniform distribution that are actually easier to find than with continuous random variables in general. Like the expectation. The expectation of x is going to be the middle value. As we've seen with distributions that have symmetry, the expectation is the value in the middle. Here, to find the value in the middle, we'll do a plus b divided by 2. To find the variance of x, yes, we can use the longer technique of finding the expectation of x squared and using the variance formula, but a standard result for the variance is going to be b minus a squared all over 12. I usually record this as the width of the rectangle squared divided by 12. And for the cumulative function, well, the cumulative function is x minus a over b minus a in between the limits a and b. So x is the variable, and really we're just trying to find the area of this blue region. So however big this blue region is, the width of the blue is x minus a, and we're multiplying that by the height, which is 1 over b minus a. So that gives us x minus a over b minus a. So let's have a look at a few examples. In this first case, we've been given a uniform distribution with limits 4 and 7, and we've been asked to find the expectation. The expectation is right in the middle of those two limits. It's the middle of the distribution. So we'll add together 4 and 7 and divide by 2. That's 11 divided by 2, 5.5. Next, we're asked to find the variance. The variance is going to be the width of the rectangle, so 7 minus 4. We'll square that and divide by 12. That gives you 9 over 12, 3 over 4. Finally, we've been asked to find the cumulative distribution function. Shouldn't be too much work to do here. The cumulative distribution function is going to be x minus a, x minus the lower limit, over the width of the distribution. So in this case, we'll get x minus 4 over 3, and the rest just fills in as usual, so zeros and ones. This function is valid in between its limits, 4 and 7, 0 when it's less than 4, and 1 when it's greater than 7. In the second example, we haven't actually been given the limits, but we've been given some information about its expectation and variance. That should be enough for us to calculate those limits. So we know the expectation of y is going to equal 1. So that means a plus b divided by 2 would have equaled 1. 1 is the midpoint of a and b. Let's write that out in one line. A plus b must equal 2. Let's think similarly about the variance. The variance of y was 16 over 3. Well, we know that must have been the width of the distribution squared over 12. I'm going to rewrite 16 over 3 as a 12 in the denominator. That means the width squared must equal 64, and b minus a must equal 8. Okay, we really have two simultaneous equations here. Let's write them one above the other. If I add these together, it should eliminate the a's. So I end up with 2b equals 10, from there b equals 5. All we need to do is to substitute that into one of the other equations, and we get our limits. So a must be -3, while b is 5. I can just check that. Is the midpoint of these two numbers, is the midpoint of these limits going to be 1? Yes, it is. Is the difference between these two numbers, the width of the distribution, the width of the rectangle, is it going to be 8? Yes, it is. I'm happy that these are the two answers. For this one, we're told that x follows a uniform distribution -4 to 6, and we're first asked to find the probability that x is less than or equal to 2.4. So let's just quickly get a sketch. Distribution goes from 4 all the way up to 6. Less than or equal to 2.4 is going to be from here. So we'll just shade off this left-hand side. So to find this probability, it's the width of the distribution, so 2.4 minus 4. Well, that will give us 6.4 over 10. 6.4 over 10, 0.64. Okay. Next, we're given this probability statement, but in the middle we have x minus 5. Either we can rewrite the distribution with some coding to be x minus 5, or we can rewrite the probability statement to fit this distribution. I'm going to do the second. I'm going to add 5 to the left, the middle, and the right. So that gives me the probability that x is in between 2 and 8. Be careful though, looking at the diagram, the distribution doesn't exist beyond 6. So there is no probability to count above 6, 7, 8. All of these values don't have any probability associated with them. This is equivalent to the probability that x is in between 2 and 6. So just be careful that your probability statement is valid for the distribution you're working with. If not, rewrite it. Okay, so from here we get the width. So the difference between these numbers is 4. 4 over 10 gets us 0.4.